So let us take a continuous B problem. So we will analyze by Kani's moment distribution. As I just now told, the first step is identifying the unknown member and forces which you have to determine. Member and forces means it is with reference to localized or generalized coordinate system. Here, this global and local are coinciding because they are all orthogonal frames. Here, each member, you have to just find out the member and moments. Only the member and moments only we select, because though shear is also there, that shear you can determine, and once you determine these end moments by applying simple equation of equilibrium. So we select only the member and moments as the unknowns, which we have to determine during analysis. This is MAB, MBA, MBC and MCP. These are the end moments which we have to determine, that we have to identify first. Then, of course, the same thing, you have to identify the member and displacements which are going to occur in the member ends. Here, this end A, it is fixed, no displacement occur. As I told you, there will be possible two displacements, because we assume members to the axial rigid. Out of two displacement, vertical displacement and rotation, both are not occurring here. Here, vertical displacement is not possible because it is a support. Here also vertical displacement is not there, only rotations are there. That we call it as theta B and theta C, only two unknown displacement. So these are unknown displacements and these are unknown forces, unknown internal member forces which we have to determine during analysis. That we have to identify first. Next, we have to determine what is known as rotation factor instead of distribution factor. As in moment distribution method, we take rotation factor here, because the member and moments which we have to determine, it is sum of the moment due to rotation and translation. Here there is no translation, we can ignore the translation effect. It is only rotation. That's why we have to determine the rotation factor. I have given the equation also how to determine the rotation factor. Using that, we have to find out the member and moments. Before finding that, we have to find the rotation factor, which is nothing but minus half into K, stiffness of that member at which we are determining the rotation factor, divided by sum of the stiffnesses of our members. So this is nothing but your distribution factor. Minus half times distribution factor, we call it as the rotation factor. That we are determining only at the continuous joints and simply supported or rigid joints. Here fixed joints, there is no displacement, that's why we don't bother about that rotation factor, because there is no rotation cost. Here continuous joints, so we will work out the rotation factor, that's continuous joint B. At this joint B, you have two members meeting, one is BA, another BC, then we determine the stiffness. That's the moment developed on account of unit rotation. So that is given by either 4A by L or 3A by L. If 3A by L, only the case of one end of the member, that is far end of the member is simply supported roller or hinge. So that is there only for the member BC. Whereas for AB, the one end is fixed, other continuous, it is 4A by L, for this it is 3A by L. Instead of the absolute stiffness, we can take the relative stiffness value, which is I by L and 3/4 of I by L. Here, for BA, it is I itself, L is 4. For BC, it is 3/4 of I by L is 3 meters, that's also I by 4. Then we have to find out some of the stiffnesses at each of the joint, that will be I by 4 plus I by 2, which is I by 2. So then rotation factor is minus half into K by sigma K. That means rotation factor of BAN, that is at this end, rotation factor is I by 4 divided by this I by 2 into minus half, that is minus 1 by 4. Same thing with respect to BC also, I by 4 by I by 2 into minus half, it is minus 1 by 4. And rotation factor at the joint C, which is simply roller joint, the distribution factor we were taking it as 1, so rotation factor will be minus half, because this rotation factor we define as minus half times distribution factor, so it is minus half. Here it is 0, that will not change at all. And another sway factor, that is displacement factor, we need not determine because it is non-sway, that we are identifying here itself. Only we have to determine rotation factor. Next step, fixed end moments, that is, I told you, all joints first we assume no displacement. So we assume each joint member to be fixed at ends, at the two ends. Whatever loading is there, due to that loading, we have to find out the moments developed, because we have to determine the end moments only to start with. These end moments will be sum of no displacement moment generated, displacement due to rotation at that end, displacement due to rotation at far end, due to sway. That's what I told. Same thing we do here now. So here first we have to apply no displacement at the joint that is fixed. So due to that, whatever loading which is there, here loading is 60 kilonewton per meter, span is 4. This moment developed in a standard formula which is already circulated to you. It is WS square by 12 for UDL. WS square by 12 means it is 60 into 4 squared, 16 by 12, which is nothing but 80. So this is anti-clockwise direction. So we take the moment developed is minus 80, because we are assuming clockwise moments are the positive one, always to start with here, as per our member or localized coordinate system. Here it is again WL by 8 because it is clockwise, so plus 80. Here it is 90 kilonewtons at 2 and 1 meter. Here the moment will be W A B square divided by L square, that is 90 into 2 into 1 squared by 3 squared, 9, that will be 20. So it is minus 20 because it is anti-clockwise. So here it is W B A squared, that is 90 into 4 by 9, that is 4 into 10, 40. 4 into 10, 40 means it is clockwise plus 40. These are the fixed end moments, that is MAB bar is minus MBA bar, that is minus 80 kilonewton meter, and MBC bar is minus 20 kilonewton meter, MCB bar it is plus 40 kilonewton meter. These are the fixed end moments which have been calculated. Now the last step let us come to is Kani's moment distribution. This is the new thing which you have to watch carefully. What is that new thing? Because all these 4 steps already it has been done in all the displacement methods earlier also. So now we will do only the distribution. Here this moment distribution we do in the form of diagram or picture, not in the form of table. So in moment distribution method, we are doing two types of moment distribution. One for non-sway, that is only for rotations. Another for translation, that is sway. And then we were adding non-sway and sway analysis. Separately we were doing. So here we do both together. So here each continuous joint as well as simply supported roller joints be represented by means of two squares or rectangles, one inscribed in the other in this fashion. Each joint, because I told you we are doing it in the form of a diagram. So in that diagram, each continuous joint, this is the continuous joint B, this we indicate in the form of a diagram in that fashion using two squares or rectangles, one inscribed in the other. This is joint B with four compartments in the space in between them. So why we are taking four means I showed you in the first example in our multi-story. At any joint in the orthogonal frame, at any joint you can expect four members meeting orthogonal. More than four you cannot get. That is left, right, top, bottom, mutually perpendicular. Any other member, it has to be inclined only, which we are not considering. That is why to represent the rotation factor in general of all the members meeting at the joint. Here at any joint there are possible, you can have four members. That is why for those four members we make provision for writing the rotation factor. Here we write rotation factor for those members which are meeting. Here at the joint B, there is a member BA. We write that BA, it is fixed. That fixed joint we don't alter at all. Same notation we use in the diagram. Fixed, and because there is no displacement, we use the same thing. Only a continuous joint and simply supported roller or whatever it is, we use this figure. C is again a roller. There again we will use either a square or rectangle type of balls, one inscribed in the other, like that. So this is the joint C, joint A, joint B, joint C. First we will write it. So suppose if you have this joint, I will indicate it like this, and all those members also on all the four sides, because all are four continuous joints. I can show it all four like that. Like that, all joints I will mark it by a diagram. Here for this example, it is only two joints to be marked like this. Then in this joint, I will indicate what all the rotation factors determined at those places. At A, rotation factor is 0. I don't write anything. At B, for BA, it is minus 1 by 4. That rotation factor, I will write it in this block towards that side. It is minus 1 by 4. For BC, again it is minus 1 by 4. I will write that minus 1 by 4. And for CB, it is minus of I told rotation factor. That I will write. So that means this entire data, whatever it was there, that I have transferred into the diagram. Next, whatever fixed end moment, that also I will write it there. MAB, it is minus 80, here it is plus 80, here it is minus 20, here it is 40. That's what I have written. So that I will enter it. So I have transferred all that calculation which I have done, except this we have to determine yet. And this I have concluded it is not sway, so it's only rotation factor to be determined, that I have determined using this diagram. That I can retain as it is, the rest I can take it out. Only this diagram I will use it now for arriving these moments. So now I have to find out MAB, MBA, MBC, MCB, these are the moments which we have to determine. So each of these moments I told you, it consists of two parts, rotation contribution at that joint itself, at each joint, and rotation contribution at further end, plus due to sway, if at all it is there, then multiply by rotation factor. So that we will start from joint to joint. To start with A. So rotation factor is not there, I need not do anything. Next I will go to joint B. That is our cycle 1. Separately I will indicate it by calculation to you. Even while answering, you can take out, write a margin and do all this calculation only for reference purpose. So cycle 1 in the joint B, rotation factor or rotation moment, that is rotation contribution moment. It is first rotation factor, which is minus half, not minus half, minus 1 by 4 for BA. Minus 1 by 4 into sum of the fixed end moment. That sum of the fixed end moment, I will write it in the central box. That is 80 minus 20 MBA plus MBC. It is 60. Here it is 40 only because it is only one member. So due to fixed end moment, whatever we got, that is 60. Then further ends, rotation at the due to fixity, that is that total rotation due to fixity of all the members meeting at the joint. Then rotation at 5 moments at the near end. So this is the first cycle, still I don't get any rotation factor, moment contribution at any near end, that will be 0 to start with. At this end, it is 0. Then rotation contribution from the further end. Further end for this member BA, it is this. So rotation factor is 0. That's also 0. So this sum is 60. 60 into minus 1 by 4, that is minus 15. That is the rotation contribution or moment due to rotation at the end B. Because whatever rotation at the end joint B is there, same rotation should be there at this end of the member by compatibility condition. Same rotation should be there. Theta B is there. So due to the theta B, this is the force generated in this member. The force generated in this member is force generated due to fixity, no rotation, force due to rotation at that end, force due to rotation at the further end, and due to sway. It is non-sway, so that sway is not coming to picture at all. I am not considering that. Then this is over. Coming to this joint. The joint, this member, BC. For this member, BC, this is with respect to AB. For BA, again we take the same moment, this remains same, total moment, that is 60 plus further end moment 0, here further end moment 0, sway moment 0. It is only 60 is the total moment. That 60 moment at the joint B, it will be shared by this member in proportion to this rotation factor. That's again 60 is the total moment, that into minus 1 by 4, that is minus 15 here. Now coming to joint C, this is joint A. Joint C, again you apply same thing, total moment at the joint C. Total moment is sum of fixed end moment. Fixed end moment, the sum of the fixed end moment we are writing in the central square block, that is 40. Sum of the fixed end moment plus moment at the further ends of the member. Here, moment at the further end you are getting now here. That is minus 15. Then moment at the other further ends, there are no members, only one member is there. That only we have to take. Sway is also not there because that member is not undergoing sway. So this is 25. 25 is the total moment. That 25 moment, whatever is coming at the joint C, that will be taken by this member in proportion to this rotation factor, that is my 25 into minus half, it is
minus
12.5 minus. So that is your first cycle rotation contribution. Next cycle, take second loop, repeat, joint A, nothing, then joint B, this is joint B, joint B, repeat, sum of the fixed and moment, 60,
plus 0.
then contribution from farther end. Now you have zero contribution, here we have contribution. Earlier first cycle it was not coming, it was 0, right, earlier. Now you are getting that you take, it is minus 60 minus 12.5, that is
47.5.
47.5 is the total moment at this. So that is the total moment at B, at the joint, on account of the loading. On account of load means this fixed end moment has come from load only I am talking about. I got this total moment. That moment will be shared by this member in proportion to that. That 47.5 into minus 1 by 4.
Minus 11.875.
11.8.
875.
That is our minus 11.9 minus 11.9. Next, joint C. So total moment 40. Then contribution from further end 11.9. That's all. The total sum is 28.1. So that is the total moment coming here. That will be taken by this member in proportion to this. It is into minus half. That is minus 14.01. So we can cancel this previous moment, whatever you got. That's all. This is the cycle 2. So you compare the cycle 2 moment with previous cycle moment. If it is not valid, you can stop your iteration work. Otherwise, continue further. Here definitely second cycle it won't converge. It is definitely you have to go for one more cycle. Go for cycle 3. This is the Kani's moment distribution of finding rotation factor. Using that formula, whatever I have given. That formula I have to remember. That I am doing here again. So start again with A and nothing. Then go to joint B and joint with sum of the fixed end moment of all members meeting at the joint. That already I have written. 80 minus 20 already I have written. That's sum of the fixed end moments due to given load. Then moment due to further end, rotation moment. That I got here, 14.1. Here it is 0. That is minus 14.1. That will be
45.9.
45.9. So that multiplied by minus 1 by 4, that is equal to minus
11.5.
11.47. 4. Yes. So that is 5 minus 11.5. This will cancel previous one. Next, coming to joint C, sum of the fixed end moment 40. Then minus 11.5, that's only forward moment, rotation contribution. It comes to minus 51.5 into minus.
So that's plus 40. Plus 40. 40 minus 11.5.
40 minus, yes, 40 minus 11.5.
28.5.
28.5, that into minus half, that is minus 14.253. Cancel the previous one. So this is your cycle 3. Again you can continue, compare these values. Again there is a difference. Continue further. I will do only for one more cycle. Cycle 4. So A joint, nothing. Then go to B joint. Sum of the fixed end moment 60. sum of the rotation contribution factor at far end, that is only minus 14.3, that is equal to
45.7.
45.7, then that is the total moment coming at B, that will be shared by these rotation factors among other members. That's 45.7 into minus 1 by 4, that is 11.5. 45, that is 5 itself, you can take it. So cancel the previous one. Then this is also minus 11.5, cancel that. Coming to joint C, we can repeat it. Sum of the fixed end moment, 40 contribution from further end, that is rotation contribution, that is 11.5. So 40 minus 11.5, that is equal to 28.5. That into minus of for this member CB, that is 14.3. So now you see the consecutive rotation moment factors, they are more or less same. There is not much variation. You can stop. This is called Kanis moment distribution. This is only a rougher kind of I made. I told you we can do it on the right side, so that at any moment if you find some doubt, you have committed some mistake, you can verify here. Where all calculations are there. Only some of the fixed end moments at each joint, some of the moment rotation contribution from further end, sway contribution. Of course, sway is not coming into picture. That's all you have to do in each and every cycle. So this you can take it out. Now you can find the final moment, MAB, MBA, and all these things. That's it, total. So you take MAB. This also I told, moment at any end of the member in local coordinates. It is given by fixed end moment at that end. That is minus 80 plus twice rotation contribution. This you have to remember. Twice rotation contribution at that end. That is twice 0, then plus rotation contribution at the further end of the member. That is for AB, further end is, or far end is B. The rotation factor you got here, that is minus 11.5. Then sway contribution. Sway contribution for AB. AB is not undergoing any sway, that is 0. So this will be minus 80 minus 7.5, that is minus 91.5, that is kilonewton meter. That's the moment you got. Then MBA, same equation, because more or less same type of equation we are getting. This is only for member individually. That for the total structure, total joint moment coming shared by rotation factor. As I told you in the beginning itself, the rotation occurs due to load in the global direction. Due to that rotation, whatever moment occurs. Then due to member, that moment you go K into D. Again we use that same type of K factors here. That is this twice we are getting mainly from that, twice near end. This is exactly slope deflection equation. 2 theta A near end plus theta B rotation at further end. Then delta 3 delta by L and MAB bar, that is fixed end. There is nothing much in this, all same type of equations we are using. That's force, displacement and their relationship. That's why it's called displacement method. Or in a different fashion we work out in diagram fashion, because no equation involved, no solution. This becomes easier. That's all, nothing other than that. MBA on same lines, MBA fixed moment, that's 80 which you have written, then plus twice the rotation contribution, twice minus 11.5, then contribution from further end, that is 0, then sway contribution is 0, so this is 23 plus 80 minus 23, that is
57. 57.
57 plus 57 kilonewton meter. Then you can find out MDC on same lines. 16 moment minus 20 twice rotation contribution twice 11.5, then contribution from forward when it is minus 14.3. So all are minus here. So this
minus
is 23, right?
Yes, sir. Minus 57.
So it is minus
57.
57. 57.3 you are getting at this now. So you write that is some variation, small variation. Of course, if you do some more cycle or this, if you calculate correct to 4 decimals, definitely you will come across this up to 4 decimal places. Correct matching, right? This also have to work out for 4 decimals. I am rounding it off. Because of the rounding off error, I am getting this. Otherwise, this MBA plus MBC has to be 0. That equilibrium condition has to be satisfied. So compatibility we have satisfied because same displacement we are taking, total joint displacement, equilibrium condition, boundary conditions also we are taking satisfying. All these 3 conditions you have to satisfy during your analysis along with that force displacement relationship. Lastly, MCB is fixed end moment 40 at that end and twice minus 2 into 14.3, then minus 11.5. So just check whether it is 0 because this is some 6 we are getting, some 0.1 difference we are getting, that you can forget it. Whatever it is, you can take it as approximately 0. Because this is 28.6, 11.5, that is 40.1 you are getting. This is 40 minus 40.1. This you are getting actually minus 0.1. That you can take it as 0. That is using this, and once you have determined this, that is what we need. You can plot the bending moment. This is the Kanis method of moment distribution. Nothing other than that. So it looks little bit confusing, I think. So that way in which you are doing, that be very clear in the mind what you are doing. That is rotation contribution, sway contribution, because only 2 displacements. That is vertical, that is sway, translation, rotation. Sway will not be there in the beams. Because it is beam problem, sway will not be there in the beam. Because reason I told you, beam ends are always held perfectly at the bottom. Ultimately it is fixed. Only columns will undergo sway. In columns we may get this kind of thing unless that along that beam level it is fixed. Along that beam level if it is fixed, that will also not undergo sway. So now in the same example we can take support settlement. So same example we do support settlement. So analyze the beam shown in figure.